Okay. So I have a couple of slides. Do you guys have these slides too? Or does it just jump into? No, you guys don't have these slides. And some of my slides are out of order for this, so you just have to bear with me. So all this is got some substances over there. And the energy required to, this goes back to the energy required to convert one mole of liquid to 1 mole of gas is here in kilojoules. Okay, that's your enthalpy of evaporation. Not sure why I put these up here. Why did I put these up here? Well, anyway, over here, now finally we have ordered pairs of the two things I just said in my introductory slide. You said that if the intermolecular forces increase, then your boiling point temperature is going to increase. Boy, that's a high boiling point temperature, isn't it? Aluminum. Let's go ahead and gasify aluminum, shall we? It's a solid now, liquefy it and gasify it. That's the temperature at which it does that. And that's how much energy you need to pump in.
That's hot.
That is hot. So all this is just basically showing you is we have an increase in boiling point temperature. We have an increase in heat of vaporization. Okay? That's all. And scientists like to do a lot of things. And one of the things is to take kind of the ordered pairs that you saw a minute ago with each substance, the heat of vaporization, boiling point temperature, heat of vaporization, boiling point temperature, and to throw them up on a scatter plot. This is a scatter plot. For about 8 months, I worked at in Morgantown, West Virginia, for the Department of Energy at a coal research facility. And I worked for a crazy Indian engineer. And he had a data bank that had, oh, I hope he doesn't listen to this lecture, but he had a data bank that had, like, you have coal, and then you have, like, you test coal for this, that, this, that, this, that, this, that, this. And you test this coal for those things. And so basically one of the things he had me do was to use some sort of statistical analysis software and to look at, basically take a pair of parameters throughout all those coals and see what I could make a straight line with. Okay? Anyway, so here's a straight line. It basically says as you increase the boiling point temperature, you also increase the heat of vaporization for a given substance. So each of those green dots is a different substance. And I'll just go ahead and tell you, we're basically going to take this information, how do I say this? Yeah, and no, that's not right. I was going to say, we're going to build up to what we call the Clausius Clapeyron plot, but actually that just looks at one substance. So these are different substances. Okay, you guys don't have this one either. Okay, so this kind of goes back to, yeah, you have it previous.
Oh,
Yeah.
okay.
Yeah, what do we mean when we say something boils at a particular temperature? Now, there's Mike. He's coming in. We basically say, now, I'm trying to, okay, this is my beaker. This is my water. Okay, I'm going to go ahead and I'm going to put it on somehow support it. What's this down here? Bunsen burner. Yep. It's like I'm playing charades. That's my Bunsen burner. Yep, I'm going to heat it up. Okay. Now, when something boils, when water boils, hey, basically what happens is the H2O on the bottom is turned from, well, because it's near the source of heat, it's turned from a liquid to a vapor, okay, and then it rises. Okay, that's boiling. So, we say that something has reached the temperature at which it will boil if oh, goodness gracious. If, I'm going to put my watch glass over here, if the equilibrium vapor pressure of the water, okay, so here you got to figure if it's simmering, what's happening is I am increasing, these are my water molecules, as I'm heating them up, I'm getting more and more water molecules, okay, in its gaseous phase. At the point at which this equilibrium vapor pressure of H2O, when that equals the pressure outside, then it will go to the phenomenon we call a boil. It will go freely from a liquid to a gas. Okay, so basically, if this is my little gas gauge here, you know what I mean, pressure gauge, when that reaches 760 millimeters of mercury, because that's about what the atmosphere is, we're running about 760. When this equilibrium vapor pressure equals 760, okay, then it's going to blow. That's it. Okay. So I have a little video to show you. But before I show you the video, I want to show you this. Now, let's see if I can like that built on there. So which line is water? Water is the black line. And actually, it didn't bother me too much, but it bothered me just a little bit. That when I was on this slide the other day, I told you the wrong thing. So let me go ahead and fix that. I kind of said that, well, let me just tell it right to you. Down here, underneath all of these curves, think of them as being a gas. And above each curve, think of it as being a liquid, final answer. And I had them actually switched around. So that's for the red line, aniline. We could find the black line. I'm going to go ahead and put liquid here for C and gas underneath. Okay. So the video I'm going to show you is actually going to take water and it's going to draw a vacuum on it. So instead of that cup of water being at 760 millimeters mercury up here, by the way, 760 millimeters of mercury, these are equilibrium vapor pressures. Go ahead and see the boiling point temperature of water. 100 degrees Celsius. All right. So let's go ahead and draw a vacuum. Let's go ahead and make it 300 millimeters mercury. We're basically going to put it in a bell jar and suck the air out. Okay, so the external pressure to that system is going to be less.
75 or something?
Yep. Exactly. It's going to boil at a lower temperature. So I just think that is so cool. So I need to go back here and see if it works for me. Oops.
Okay, so food coloring is mixing around in there, and